Section 4.2 talks about the information we can glean from the derivative. It's what the derivative explains for us. And the first theorem talks about what the derivative tells us when it's positive or negative. It says that if the derivative is positive, the graph is increasing there. And if the derivative is negative, the graph is decreasing there. So if I pick an x value and plug it into the derivative and I get a positive answer out, well, since it was in the derivative, which was the slope of the tangent line, then that positive answer tells me the slope is positive. So the graph is moving in a positive direction. And if I plug it into the derivative at that point and I get a negative number, it means the slope of the tangent line is negative there, and the graph is moving in a negative direction. And here's a picture to describe it, and a little key on the right. It says that if f prime is positive, that's where it's increasing, that's the green highlighted area here. And if f prime is negative, that's where the graph is decreasing. Now this is the graph of f of x. This is not f prime. This is the graph of f of x. But notice when I take the derivative, if the number is positive, I know the derivative is going to be positive in this green area because the graph is increasing there. And I know the derivative of f, whatever it is, will be negative in the yellow area because the graph is decreasing there. And these points where the derivative is 0, and the reason the derivative is 0 is because if you look at the tangent there, you get a horizontal line. And the slope of a horizontal line is 0, so the slope of the tangent line should be 0. So the derivative should be 0 there. These x values are called critical points. And we use those to figure out hills and valleys. And so the first example is to sketch a graph with the following characteristic. And it says that f prime of negative 1 is undefined. So the derivative is undefined at negative 1. And the derivative is positive from negative infinity to negative 1, and negative from negative 1 to infinity. So if I'm going to graph a graph that has these characteristics, there's a couple things that I need to have. The first one says the derivative is defined at negative 1, undefined at negative 1. There's a lot of ways I could do that. There's many ways. There's more than one. But the easiest way to do that would, now remember I'm drawing the graph of f here, and I'm just knowing what the derivative tells me. Remember where the derivative is positive, that means the graph is getting bigger from left to right. It's increasing from negative infinity to negative 1. So this graph has to be getting bigger on the left of negative 1. And since the derivative is negative from negative 1 to infinity, that means the graph is decreasing to the right of negative 1. So over here it decreases, and over here it increases. So I have to get bigger and smaller. The trick is, at negative 1, I need the derivative to be undefined. Well, there's lots of ways to do it. The easiest way is a vertical asymptote. If there's a vertical asymptote in the original function, then the derivative will be undefined there too. It'll have a vertical asymptote as well. Like 1 over x, the derivative is negative 1 over x squared. You'll notice that graphs keep vertical asymptotes. So I need this to be increasing over here on the right, so I just draw it getting bigger. And I need it to be decreasing on the left, so I draw it getting smaller. So here's a graph that has those characteristics. Notice it increases to the left of negative 1, which is what the derivative being positive there tells me. And it decreases to the right of negative 1, because that's what the derivative being negative tells me. And being undefined at negative 1 tells me that there's something happening. A sharp corner could happen there. You could also connect this with a sharp corner. That would work as well, because at sharp corners derivatives don't exist. Or you can do it with a vertical asymptote. So here's another example of a graph that would actually work. Sharp corners derivatives don't exist as well, and the reason why is if you think about the tangent line, you don't know which way to define it. You get all confused over which one to take. You can think about it crossing through infinity in the middle, but you don't know which tangent line to use at a sharp corner. So there's another version of a graph of f of x that would have worked. Vertical asymptotes and sharp corners are where the derivative is undefined, usually. And here they're asking me to actually find the intervals where it's increasing and decreasing. And so to do that, I have the function. If I want to figure out where it's increasing or decreasing, I have to look at the derivative. The derivative is positive, it's increasing. The derivative is negative, it's decreasing. So first I take the derivative of this function. In this case, it's negative 2x. Now that's defined everywhere. So I just need to figure out where that... So there you could have problems. If it's not positive, it could be undefined or it could be 0 if it's not positive or negative. So I'm going to look for the place where the slope is 0. to figure out where it's neither positive nor negative, right? Where the first derivative is positive, it's increasing. Where it's negative, it's decreasing. So I'm going to figure out where it's 0. Figure out where it's not changing at all, where it's not positive or negative. And I divide by -2 and I get x equals 0. This is called the critical point. And we'll talk about that in a moment. But to figure out where it's increasing or decreasing, I'm going to look at the derivative. Because the derivative tells me whether the function is increasing or decreasing. And I know at x equals 0, it's doing neither. Because the derivative equals 0 there. Those are those critical points we mentioned before. Places where the derivative equals 0. It's not increasing nor decreasing there. So I find that place. It's at x equals 0, and I'm going to test around it. I'm just going to pick some numbers that live around 0. -1 to the left, 1 to the right. And I'm going to plug them in to the derivative. When I plug -1 into the derivative, I get 2. When I plug 1 into the derivative, I get -2. So that means it's positive in the area where -1 is, because 2 is a positive number. And it's -1 in the area where x equals 1 is. Or it's -2 in the area, it's negative in the area where x equals 1 is, because notice -2 gave me a negative number out. So I know that the graph is increasing, so f of x increases, and that's where it's positive, -infinity to 0. Notice it doesn't include 0, because at 0, it doesn't increase nor decrease. And it decreases from 0 to infinity. So we figured out the intervals of increasing and decreasing. We can do the same thing with this function. We're going to figure out where the derivative is 0, or it's not doing either, put it on a number line, and check to figure out where the derivative is positive or negative. So first I find the derivative. Now I don't have to worry about vertical asymptotes or anything like we had in the picture. I just got to figure out where the derivative is 0. And then I can test around it to figure out where it's positive or negative. So I get 3x squared equals -4. X squared is -4/3. And that's a -4/3. So when I take the plus or minus square root, I get an I in there. This is 2 over root 3 I. And I doesn't exist anywhere on the number line. So when I go to draw a number line to test where the derivative is increasing or decreasing, there is no critical point. There's no place on the number line where I can plot this. So that means it's the same the whole time. So I can pick any number I want. Hell, I'll pick 5. So I plug 5 into the derivative just to see what's happening there. I get 25 times 3, which is 75, plus 4, I get 79. That's a positive number. So I know the derivative is positive the whole time. You can also see by looking at it. X squared is always a positive number. 3 times x squared will still be positive, and I'm just adding 4 to it. The derivative is always positive, everywhere. It's never 0, because I got an I when I tried to find that. So I know that this function is increasing the whole time. Because there's no place where the derivative is where the derivative equals 0, and the derivative is always positive. So here's another one. This one is actually giving us a bounded interval, so we don't go on forever. But it's I have cosine squared of x on -pi to pi. Figure out where it's increasing or decreasing. So we have to look at the derivative to find out about increasing or decreasing. And remember, cosine squared of x is really just cosine of x squared. So when I take the derivative, I have to use the chain rule. This is 2 times the cosine of x to the first. That's the derivative around the box. And the derivative of cosine is negative sine. So I get -2 sine x cosine x. Now there's no vertical asymptotes in sine or cosine. So to figure out where the derivative is 0, I just set it equal to 0. This will tell me where it's not changing, where it's not increasing or decreasing. And so in this case, -2 can't be 0. So it's either the sine of x or the cosine of x that equals 0. Well, this is -pi to pi, so if you think about the unit circle. From -pi to pi, -pi is down here, or -pi is here, Positive pi is here. That's the whole circle. So this is all the places it equals 0, but we got to think about this as negative pi, 0, and pi. So where's the sine of x 0? The sine of x is like the y, so the sine of x is 0 here and here. That's where the sine of x is 0. And so if I look at those points, I think that's negative pi and 0 and pi. So this happens at negative pi and 0 and pi. Where does the cosine x equal 0? Here and here. Well, this is 3 pi over 2, but I got to think about this as negative pi. If that's negative pi, then that's half a negative pi. Negative pi over 2. And pi over 2. Those are my critical points. So I put them on a number line. Negative pi over 2, 0, pi over 2, and pi. And I'm plugging these in to the derivative, which is negative 2 sine x cosine x. Well, when I plug points in, it can help to think about the unit circle as well. A point between negative pi and negative pi over 2. This is between negative pi and negative pi over 2. And we know at the pi over 4 points, we get root 2 over 2 when we plug in sine and cosine for any pi over 4, 45-degree reference angles. So the one over here, when I plug it in, the cosine will be positive root 2, or negative root 2 over 2, because it's on the left side where x is negative. Cosine is like x. So cosine will be negative root 2 over 2, and sine will also be negative root 2 over 2. We're in the third quadrant. So when I multiply them together inside here, this is negative pi, 3 pi over 4 is where it turns out to be. When I put those in, it'll be negative 2 times negative root 2 over 2 times negative root 2 over 2. My answer will be negative. And then I'll have, one of those 2's will cancel, I'll get 1, negative 1. But it's a negative number in there when I plug it into the derivative. That's negative 3 pi over 4. These are my critical points. I'm going to put circles around them so I remember. This is where there's no change, and so I put circles around. Between 0 and negative pi over 2, I could plug in negative pi over 4. Remember, it's root 2 over 2, root 2 over 2 again, except now the cosine will be positive because the x value is positive. The sine will be negative. So if the cosine is positive but the sine is negative, then it'll look like this. This will be at negative pi over 4. At negative pi over 4, the cosine is positive root 2 over 2. The sine is negative root 2 over 2. When I multiply this all together, the two negatives make it a positive 1. So it's the same answer, but in here it'll be positive. Then I can plug in pi over 4. At pi over 4, sine and cosine are both root 2 over 2. So they're both positive at positive pi over 4. When I multiply those together, I get a negative answer because of the negative 2, which means the derivative is negative in there. And then I can do 3 pi over 4. I'm just using reference angles to help me figure out points that I can easily figure this out for. Here the cosine is negative because the x is negative. The sine is positive because the y is positive. So at 3 pi over 4, positive 3 pi over 4, the cosine, or the sine is positive. The cosine here is negative. When I multiply all that together, I get a positive 1. So I know that the graph is increasing where the derivative is positive, and that happens from negative pi over 2 to 0 and pi over 2 to pi. And it's decreasing where the derivative is negative, and that happens from negative pi to negative pi halves, and pi over 2 So I'm doing decrease, yeah. 0 to pi over 2. So figuring out where it increases or decreases amounts to looking at the derivative and finding points inside these test intervals to see whether the derivative is positive or negative. Where the derivative is positive, it's increasing. Where the derivative is negative, it's decreasing. Also note I didn't include these critical points in my intervals here because at negative pi over 2, the derivative equals 0. That's how I found these points. So in this case, these points, it wasn't changing at all. The derivative was 0 there, so I don't include them. So what do we just do? We found intervals where f of x is increasing or decreasing. And what we do is we figure out where the derivative is 0 or undefined. Those are called the critical points. And we put them on a number line. And we test a point in each interval around those critical points. And we plug that test point into the first derivative. And if the first derivative is positive at that test point, then the function's increasing at that interval where you tested. If the derivative is negative at that test point, then it decreases on that interval. So the first derivative test, so that's a way that we can figure out how the functions are increasing or decreasing. Notice I had cosine here. That's why they bounded the interval. Otherwise, cosine and sine would go on forever. So here are a few examples of how this increasing, decreasing works. And the first derivative test is a way you can tell whether your critical points are places where maxima or places where minima occur. And what it says is if x equals c is a critical point. So I have some critical point on a graph. And let's look at one. This would be a critical point. I'll call it x1. And this would be a critical point. I'll call it x2. Notice as the function increases to the right of the hill, at the top of this hill, this is a maxima. It's a local maxima. And if you'll notice, to the left of it, the function is increasing. And to the right of it, the function is decreasing. And this is what the first part says. If the derivative changes from positive to negative, over here the derivative is positive, over here the derivative is negative. If it changes from positive to negative, if it goes from increasing to decreasing, you reach the top of a hill. You walked up the hill and now you're sliding back down it. That's what the first one says. So it has to be a local maxima if the derivative goes from positive to negative around a critical point. If it changes from negative to positive, you're at a local minima. And the reason why that happens is because when it's negative, you're sliding down the hill, and then it changes to positive, which means you're walking back up the hill. So you slid down the hill, and now you're walking back up around that critical point. So that's all the first derivative test tells us. And so if we were to go back up here, we would know that the cosine squared of x between negative pi and negative pi over 2, it's decreasing. From negative pi over 2 to 0, it's increasing. We know that's a local minima happening here because of the first derivative test. And in between negative pi over 2 to 0, it's increasing. From 0 to pi over 2, it's decreasing. You can see that that's a local maxima by the first derivative test. So you can use this number line to tell whether those critical points are maximas or minimas. Negative pi over 2 has a minima, pi over 2 has a local, or 0 has a local maxima. Negative pi over 2 will have a local minima because of the way it's increasing and decreasing. That's what the first derivative test does for us. It lets us figure out the shape of the graph. So here's an example of this. Locate all critical points and use the first derivative test to find the max and min. So here I have x times the square root of 9 minus x squared, which is going to be a not very fun derivative. I'm going to rewrite it so it's a little easier to take the derivative of. Because to take the derivative I need the chain rule. Or the product rule, I'm sorry. I need the chain rule too. But the product rule is what I have to use to start this off. Take the derivative of u, I get 1. Take the derivative of v, now this is the chain rule. I get 1/2 9 minus x squared to the negative 1/2 times negative 2x. And if I write that out, and cancel the 2's. This will make it easier for me to simplify stuff in a sec. The negative x is on top, and that negative 1/2 means it's a square root. The negative means it's on the bottom. The 1/2 means it's a square root. The negative means it's on the bottom. So the derivative of this thing is uv prime, that's negative x squared, over the square root of 9 minus x squared. And check these. U times v prime, those x, negative x and x, give me negative x squared, plus vu prime. Remember, 9 minus x squared to the 1/2 is just the square root of 9 minus x squared. Here's my derivative. Well, I know this thing is undefined where 9 minus x squared equals 0. It's undefined there. The first derivative is undefined there. So these are critical points. Where the first derivative is undefined is critical points. Well, the other critical points I get are where this thing equals 0. And what I can do is I can clear the denominator on this. I can multiply everything I see by the square root of 9 minus x squared. See if I can fit this in here. Yeah, there we go. Notice this square root of 9 minus x. I multiplied everything by the same thing. This is called clearing the denominator. And notice the square roots cancel there. And so what I end up with is negative x squared. This is the square root of 9 minus x squared times the square root of 9 minus x squared. That's the square root of 9 minus x squared squared. Which is just 9 minus x squared. 0 times anything is 0. Negative 2x squared plus 9 equals 0. 9 is 2x squared. 9 over 2 is x squared. Plus or minus 3 over root 2 is x. The square root of 9 over 2 is 3 over root 2. So these are my other critical points. Plus or minus 3 over root 2. And those critical points come from where the derivative is 0. So I got my critical points. Now I can put them on a number line. Negative 3. Negative 3 over root 2. 3 over root 2. And 3. I'm going to put little circles around them to remind me that's where it's undefined or 0. It's neither positive nor negative. And then I go and test. Where do I test? I test in the derivative. What does the derivative look like? It's big negative x squared over the square root of 9 minus x squared plus the square root of 9 minus x squared. That's the derivative. I'm checking for increasing, decreasing. So, if I plug in negative 3 into the derivative, it's undefined because I get a 0 in the bottom. What if I take a point like negative 4? If I plug negative 4 in there, I get the square root of 9 minus 16, which is the square root of negative 7. That's root 7i. I can't graph that in either place. This is not part. I can't figure anything out here. It's actually because this isn't part of the domain. Notice if you put negative 4 into the original function, you get negative 4 times root 7i. That's ungraphable there. The domain of this thing actually works from negative 3 to 3. That's actually the domain of this graph. But you get stuff with i's in it when you plug in negative 4. So we know at negative 4, since I get stuff with i's in it, there's no increasing or decreasing going on there. We can't even figure out what that means. Now we pick another test point. This one will actually be in the domain. The other test point has to be between negative 3 and negative 3 over root 2. So to do this, you got to figure out what negative 3 over root 2 is. So just get a calculator. Into your calculator, you type negative 3 over the square root of 2, and you get 2.12. So that's like negative 2.12. So how about negative 2.5? I'm just going to plug it in and see what I get. Plug it into the derivative. F prime of negative 2.5. So I get negative 2.5 squared divided by the square root of 9 minus 2.5 squared plus the square root of 9 minus 2.5 squared. And that gives me negative 2.11, which is negative. And since it's the derivative, it tells me it's decreasing there. Pick a number between negative 3 root 2 and positive 3 root 2. 0 is the easy one. Plugging 0 in here, I get negative 0 squared over the square root of 9 plus the square root of 9, which is a positive 3. So that tells me the derivative is positive on that interval, which means it's increasing. And then I plug in a positive 2.5. Notice I get the exact same answer as I did when I plugged in negative 2.5. Negative 2 because all the x's are squared in that equation, so whether you use a positive or a negative, it doesn't matter. You'll get the same answer out because the square takes care of the negative part. But you should plug that into your calculator and check. You'll see you get negative 2.11 when you plug in 2.5. If you were to plug in negative 4 or 4, which could be another test point you use out here. Notice in both cases when you plug them into the derivative, negative 4 squared is 16. But notice in here, you get the square root of negative 7, which is root 7i. And the same thing happens when you plug in 4. You actually get the exact same thing because all the x's are squared. The same problem happens when you plug in 4. That tells you that out there is no increasing or decreasing property. It's outside the domain of the actual function. But now I know from the first derivative test that this was decreasing, then increasing. So that has to be a minima, a local minima. And that happens at negative 3 root 2. This was increasing and then decreasing. So it must be a local maxima happens here. So I figured out a bit about this. I'm going to erase this part here that has me solving the derivative. So I have that it's increasing where the derivative is positive. That's negative 3 over root 2 to 3 over root 2. It's decreasing where the derivative is negative. And that happens from negative 3 to negative 3 root 2. And from 3 root 2 to 3. I know that there's a local maxima. To find the maximum value, I have to plug it into the function, but it happens at x equals positive 3 over root 2. That's where the local maxima is. To find the local maxima, I have to put positive 3 root 2 into the original function to figure out what it was. So I do that. F of 3 over root 2 equals 3 over root 2 times the square root of 9 minus 3 over root 2 squared. Because that's where the local maxima occurs. So I type this into my calculator. You get 4.5. Notice I plugged it into the original function to find the maxima. Then there's a local minima of, this will happen at x equals negative 3 over root 2. Figure out the local minima, I plug negative 3 root 2 in there. And when I do that, I end up with negative 4.5. And the reason why is the x squared won't change what happens under the square root, but the negative will just make that negative 3 root 2. So I figured out all the increasing, decreasing local maxes and local mins, and where they occur. Notice when I get i's out of my answer, then I don't have to worry about that as an increasing or decreasing part of the graph. Usually it's because it's outside the domain of the graph. Well, we can do stuff with the second derivative too. It's called the concavity, and it tests the bowl shape of a graph. Concavity is a bowling shape that's up or down. And to find about the concavity, you need to look at the second derivative. And this is very similar to the first derivative. It's really the same concept. You're doing the same thing. We just call it different names. Where the first derivative is 0 or undefined, we call those critical points. Where the second derivative is 0 or undefined, we call those inflection points. When the first derivative is positive, the function is increasing. When the second derivative is positive, it's concave up. And here's what concave up looks like in a picture. Notice if you had to fill it with water, it would hold the water. It's a bowl facing upward. If the first derivative is negative, the function is decreasing. If the second derivative is negative, the function is concave down. And notice concave down is a bowl pointing downward. So if you put water in it, it would fall out. So this is very analogous to the first derivative. Critical points where the first derivative is 0 or undefined. Inflection points where the second derivative is 0 or undefined. First derivative positive, increasing, negative, decreasing. Second derivative positive, concave up, negative, concave down. And here's a picture of a graph where you can see these kind of in action. In the green, the second derivative is negative because the graph is concave down. It kind of looks like a bowl that couldn't hold water. And in the yellow, the second derivative is positive. The green, the second derivative is negative because it's a bowl that can't hold water. It's concave down. In the yellow, the second derivative is positive because it's a bowl that can hold water, and it's concave up. And notice where these bowls change over from not being able to hold water to being able to hold water, concave down to concave up. Where concavity changes, that's what the inflection point tells us. And it's hard to visualize that sometimes. Sometimes you can't really look at a graph and easily tell where the inflection point is going to be, just because of the shape and the nature of the graph, or how zoomed in or out it is. But if you use calculus, you can find exactly where the inflection point is, just by setting the second derivative equal to 0, or finding out where it's undefined. Notice the process is exactly the same as it was for increasing, decreasing. Concavity is the exact same process. First you find the inflection points and put them on a number line. You test a point each interval around the inflection points and plug them into the second derivative. The second derivative is positive, it's concave up. The second derivative is negative, it's concave down. And so let's look at an example of this. It's 5x to the fourth minus 20x cubed plus 10. We're going to find all the inflection points. We're going to figure out where it's concave up and where it's concave down. Exactly like the first derivative stuff we did, except now we're going to be doing it with the second derivative. So what do? I take the derivative twice. The first derivative is 20x cubed minus 60x squared. The second derivative, which is what I need to work with to figure out about concavity and inflection points, is 60x squared minus 120x. That's defined everywhere. There's no place where it's undefined. So I'm just going to set it equal to 0. I can factor out a 60x, and I get x minus 2 when I do that. And so I get either x is 0 or x is 2. These are my inflection points. They're where the second derivative is 0. When the first derivative was 0, those are critical points. Where the second derivative is 0, those are inflection points, also undefined. So now to figure out about concavity, I do just what I did with the first derivative before. Now I do it with the second derivative. I plot my my inflection points, 0 and 2, and I put little circles around them because it's 0 there. It's neither concave up nor concave down there. I'm looking at the second derivative when I'm plugging this stuff in. 60x squared minus 120x. And I pick some test points. The first one is maybe -1. I'll pick 1. I'll pick 3. I'm going to plug these into the second derivative. When I plug in -1, I get 60 plus 120, which is 180, which is a positive. So it's the second derivative now. I know it's concave up here. I plug 1 into my second derivative. I get 60 times 1 squared minus 120 times 1. That's negative 60. The second derivative is negative, so it's concave down. In the second derivative, I plug in the last test point, which is 3. So I have 60 times 3 squared minus 120 times 3. And I get 180, which is a positive. So that tells me the second derivative is positive, so it's concave up there. So now I know concave up, that happens where the second derivative is positive. So from negative infinity to -1, and from 2 to infinity. And concave down is where the second derivative is negative. And that happens from 0 to 2. So notice it's exactly like what we did before with the first derivative, except now we're doing it with the second derivative and we're calling them different things. Inflection points, concave up and concave down. But now I know a lot more about this graph. I know that where it's concave up, this graph is going to have a shape that bowls up. So it has to be a graph that points up and down and back up. So I get an idea of the shape. This is not the exact graph, but this gives you an idea of the shape of the graph. Notice it's a bowl opening up. In the yellow spots, and it's a bowl opening down in the green spots. So it just gives you an idea of the shape of the graph. It helps you figure out what it's going to look like. And we can do another one of these. This is another concavity type problem. Here the derivative's a little trickier. So if you want to figure out where it's concave up, concave down, we got to find the derivative twice. This is a good one because natural log can intimidate people, but natural log's not bad. To do the derivative of a natural log, you just put what you're taking the natural log of, the argument on the bottom, and you put the derivative of that on top. That's the whole trick to natural logs. So there's the first derivative. But I need to find the second derivative. So I'm going to rewrite this so I don't have to use the quotient rule. I don't really like the quotient rule. So I can write the denominator as that to the negative first power, and then I can do u and v. U will be 6t, and v will be 3t squared plus 1 to the -1. Well, u prime is going to be 6, and v prime is going to be negative 3t squared plus 1 to the -2 times 6t. And if I write that out so it's a little more simplified, it's 6t times, oops, wrong symbol, 3t squared plus 1 squared on the bottom. And so I can do uv prime. Notice 6t times -6t is negative 36t squared. Over 3t squared plus 1 squared. Plus vu prime. V is 3t squared plus 1 in the denominator. That's v. And u is u prime is 6. Now notice that derivative is defined everywhere. So we got u v prime. v times u prime. Yep. Notice 3t squared is always positive, so 3t squared is always positive, and 3t squared plus 1 is always positive, and it's never 0, because you're always adding 1 to a positive number. So this function is defined everywhere. You don't have to worry about any places where it's undefined. So to work this, you just have to set it equal to 0. And a lot of times people have trouble solving equations like this because they have this stuff called fractions that nobody likes. I'm going to leave some space here because I know what I'm going to write. We want to set it equal to 0. The trick is to clear the denominator. The common denominator here is 3t squared plus 1 squared. So what I do is I multiply everything by that common denominator. This works very well when it's equal to 0, especially. And a lot of times that's what you're doing in calculus. But I mean, it works when it's equal to other numbers as well. So over here, this is really over 1, and it cancels the denominator. Over here, one of them cancels the denominator. Over here, that's just 0, because 0 times anything is 0. And so I end up getting negative 36t squared plus 6 times, there's still a 3t squared plus 1 that didn't cancel, equals 0. Much easier to solve. Negative 36t squared plus 18t squared plus 6 equals 0. Negative 18t squared plus 6 is 0. So 6 is 18t squared. 1/3 is t squared. So t is the plus or minus square root of 1/3. Or plus or minus root 3 over 3. So I figured out the inflection points. That's what I found right there, were the inflection points. So now I take those inflection points and I put them on a number line. The first derivative is right above the number line here. I get negative root 1/3 and root 1/3. Little open surface, neither increasing nor decreasing. And I want to test them in the second derivative. So maybe negative 1. Let's see, what is root 1/3? That's 0.57. Just to give you an idea of if it's legal to plug it in. So I plug negative 1 in there. When I plug in negative 1 into the second derivative, because I'm testing concavity, I got, let's see, this is negative 36 over 4 squared plus 6 over 4. You plug in negative 1, you get negative 36 over 3 plus 1 squared, 4 squared. Or negative 36. So negative 36 divided by 16 plus 6/4 gives me negative 0.75. So it's negative I can pick 0 to plug in. The first one gives me 0 over 1 plus 6 over 1, which is 6, which is positive, the second derivative. And I can plug in the number 1. And when I plug in 1 into the second derivative, I get negative 36 over 4 squared plus 6 over 4, which is negative 3/4. So I get a negative number when I plug in 1. So now I know all the concavity of this graph. I know that it's concave up, where it's positive. That's negative root 1/3 to root 1/3. And it's concave down when it's negative, which is negative infinity to negative root 1/3, union root 1/3 to infinity. Oh, and there's the inflection points. So that would solve the problem. You found all the inflection points. and you figured out where it's concave up and concave down. And you can use the second derivative to tell you whether you have local maxima or minima at a certain critical point too. What the second derivative test tells you is if you take the second derivative and you find the critical points, which is where the hills and the valleys occur. You remember the critical points are where the first derivative is 0 or undefined. That's where the top of the little hills or the bottom of the valley show up in the graph. If you were to take your critical point and plug it into the second derivative, you'd be able to tell whether it was a max or min just by knowing the concavity there. If your critical point was in a place where it was concave down, then your critical point would have to be a maxima, because it's concave down in there. If your critical point is at a place where the graph is concave up, it would have to be a minima, because the bowl points up there. And that's what the second derivative test tells us. Take the critical point and plug it into the second derivative. If the second derivative is positive, it's a minima, because it's concave up, so it's the bottom of the valley. If the second derivative is negative, it's a maxima, because it's concave down there, so it's the top of the hill. And so let's do an example like that. It says locate all critical points, and then use the second derivative test to determine whether max or min. So to find critical points, that's where the first derivative is 0 or undefined. So to find critical points, I take the first derivative. 6x squared minus 6x. That's defined everywhere, so I set it equal to 0. I can factor out a 6x. I'm left with x minus 1. So I get that x is 0 or x is 1. Those are my critical points. Now to use the second derivative test, what is this test for, the second derivative test? Well, it tests to see if maxima or minima occur at these critical points. So to use the second derivative test, I have to take the second derivative, which is 12x minus 6. And then I test my critical points that I found before. I plug in 0 into the second derivative. That tells me it's concave down. So at that critical point, the graph is concave down. So it has to be a maxima, since it's concave down there. It has to be the top of the hill. So there has to be a local maxima at x equals 0. At that critical point, it has to be a maxima. And I can take my second derivative and plug in my other critical point, 1. I get 12 times 1 minus 6, which is 6. That means it's concave up there. Well, you have a critical point, and the graph is concave up. That means that critical point had to be a local minima, had to be the bottom of a valley. So there's a local minima at x equals 1. It's not a great idea to try to memorize these. You should really try to think about why it's true, especially with the second derivative test. It's not too bad if you can conceptualize it.